Welcome to week 6. This week, we're talking about templates. While we've been using templated objects in previous examples and projects, this week we'll take a look at how to create templated functions and classes of our own. Templates are another one of those C++ features where there can be a lot of confusion and complexity in advanced uses of the feature, while the core functionality is simple. In a word processor, a template is a starting point for a document that you can fill in with your own details to turn it into a final, usable document. In a similar way, a C++ template is a piece of incomplete code with placeholders for types or values. Users of a template provide the template arguments that fill out these placeholders to get complete, usable code. This gives us a powerful way to write generic code that can be reused with different types. Here's a simple example where we have an average function written for integers, and we're trying to get the average of two doubles. Given the values of 0 and 5, we'd expect average to give us 2.5. Unfortunately, our average function only knows how to handle integers, so integer division gets used and we get 2 instead. We could write a new overload of average that works with doubles, and more overloads for every other type we might want to take the average of. This would leave us with a lot of duplicate code though, since every implementation will be basically the same except for the types. This is a great situation for using templates. And this is the templated version of our average function. Every template starts with the template keyword, followed by the template parameter list in these angle brackets. Each template parameter is a placeholder for a type or value. We can use the parameter name in the templated code, and it will get replaced by the real type or value provided by the user of the template. The type name keyword here tells us that this placeholder is meant for a type, not a value. You'll also sometimes see the class keyword used here to mean the same thing. In this case, because we give double as the template argument for this use of average, each of the t's gets replaced by double. The average function uses floating point division, and we get 2.5 just as we expected. The next line uses int as the template argument, and we see the same behavior we had when the function was written using ints. That's because it is essentially the same function. Each t gets replaced by int for this version of the templated function. Let's open this example up in C++ Insights to get a better sense of what's happening. Insights shows us that the compiler is creating two new copies of our average function, one that uses double everywhere and one that uses int everywhere. These are called specializations. A specialization is the code generated by a template when the template parameters are all replaced by the real types and values. Every set of template arguments we use creates a new specialization. We can write specializations ourselves when we want a function to behave differently with a specific type, and this is exactly how we would write them. We still use the template keyword, but instead of having parameters in our template parameter list, we have arguments in a new set of angle brackets after the function name. And just so you know, these if-def macros are just part of C++ Insights. They're not a required part of writing template specializations. Of course, templates aren't limited to functions. We can create template classes as well. Here's a short example with a templated struct called holder. The type of the data member is determined by the template argument t. One way to confirm to ourselves that data is an int is to try to shove a double value into it and see what we get when we print it out. What we see is we get the truncated integer value of the double we put in. Looking at this code in C++ Insights, we again see that a specialization of our template has been created to support our use of holder in the main function. Just like we saw with functions, the specialization replaces the placeholder t with int throughout the specialized class definition. One important side effect of this specialization step in compiling templates is that the parts of our code that use the template need to have access to the full definition of the template class. We can't separate function declarations from function definitions with templates if we want users of the template to be able to give us any arbitrary arguments. The code that uses the template needs to be able to see the definition so it can do the replacements needed to build the specialization. So what does this mean for our day-to-day code? Well, it means we often don't have an implementation or .cpp file for templated classes or functions. The entire class and all of its member functions will be defined in the header file. Thus, everyone that includes that header file gets the whole class definition and can create any specializations they want. This is one reason you'll often see template-heavy libraries shipped as header-only libraries. There's one more thing I'd like to cover about templates today. That's non-type template parameters. Our examples so far have used the typename keyword to declare template parameters that expect a type. We can also declare template parameters that expect a value instead. In this example, I've added a second template parameter called printCount that takes in an int which is used in the new print function to determine the number of times data is printed. Now when we use holder and need to create a specialization of it, we have to give it the type of data and an integer value for that printCount parameter. You've used non-type template parameters before when using the standard array container. The first argument sets the type to be stored in the array, and the second sets the size of the array. The std_array class is templated in about the same way our holder class is. And now you know a bit more about what that actually means under the hood. To be clear, we've just scratched the surface of what you can do with templates in C++. There are a lot of things templates can do and patterns they can be used in that enable some pretty magical code. For now though, you've got a handle on the fundamental functionality of templates and how they enable us to write generic code.